Are you viewing this one on slideshow? Or is
Yes,
it?
Miss.
Okay, thank you. So we are now on the second example on reactors, multiple reactors in series and in parallel connections. And this is our second sample problem. So we'll start with this. Now, the elementary irreversible aqueous phase reaction of A reacting with B, 1 mole for each, forming R and S, is carried out isothermally as follows. So equal volumetric flow rates of two liquid streams are introduced into a 1 cubic feet mixing tank. So one stream containing 0.020 mole A per liter and the other 1.4 mole B per liter. Now the mixed stream is then passed through a 4 cubic feet PFR. Now we found out that some R were formed in the mixing tank. So before the PFR, there is a mixing tank for these two streams containing separately A and B. Now the concentration of R that was formed is 0.002 mole R per liter, which makes the mixing tank function like a backmix reactor or a CSTR. So the mixing tank is to be viewed now as a CSTR. What is the concentration of R at the exit of the PFR and the conversion of A in the system? Okay, so this is our problem. So please get a screenshot of the problem. That way you can contribute later. We'll have a healthy discussion on the solution that will be started and shared to you in the Jamboard. Okay, so please take a screenshot of this. Okay, and then we'll have the Jamboard. Wait, okay, so I hope you can see the Google Jamboard. Can you see the Google Jamboard?
Yes, Miss.
So this is our second sample problem. So originally, we are to mix two separate streams containing A and B, but it so happened that in the mixing tank, some R is formed. So now we can view the mixing tank as a CSTR. Then this CSTR, this mixing tank, is followed by a PFR where more R is to be formed. So this is our mixing tank slash CSTR. So you have this particular stream and another stream. So you have two separate streams in here. And the stream leaving the CSTR is introduced into a PFR. Okay, so basically this is our system. Now we have two streams being mixed here in our CSTR. So we have CaO. What's the initial concentration of CaO? Did you take a screenshot of the problem? What's the initial concentration of CaO?
0.02, Miss.
Okay, it's 0.02. Thank you. Thank you. So this is 0.020 mole A per liter. So this other stream must be for B, and for CBO, we have 1.4 mole of B per liter. Now, for this mixed flow reactor, mixing tank, aka mixing tank, we have the volume to be at 1 cubic feet. Now, this particular CSTR had the formation of R. So let's say we'll label CR prime. the amount of R produced in here is, how much is the R being produced from the mixing tank or from the CSTR?
0.002.
It's 0.002 mole R per liter. Now, for our plug flow reactor, the PFR, so we'll have its volume labeled as V sub P. We have it at 4 cubic feet. Okay. Now, what does it say about our reaction? What is our reaction? An elementary, irreversible, aqueous phase reaction. So since it's an aqueous phase reaction, we have the fractional change and the volume equal to 0 because this is a liquid phase reaction, and you are provided the stoichiometric equation. Okay, so you have 1 mole of A reacting with 1 mole of B, forming 1 mole of R and 1 mole of S. And since this is an elementary aqueous phase reaction, so we say that the rate in terms of A, which we could say also the rate in terms of B, or the rate in terms of the formation of R and S is equal to KCACB. It's elementary, and as such, we base our rate law on the stoichiometric equation itself, which actually is 1 mole of A reacting with 1 mole of B on the left side, because we base our rate law on the left side of our chemical reaction. This K depends on where do we base our rate. So if this is in terms of rate, if the rate is in terms of A, this would be K sub A. If the rate is in terms of B, this would be K sub B, and so on and so forth. So K is dependent on what particular species was used as a basis for the rate law or for the rate of the reaction. Now, it was also mentioned in the problem, it's worth noting that equal, so there is second statement, it says equal volumetric flow rates of 2 liquid streams are introduced into 1 cubic feet mixing tank. So we have equal volumetric flow rate, so we can write this one as, say, V sub A, and this is V sub B, and we can write here V sub A plus V sub B is equal to V, wherein V sub A is just equal to V sub B. It's because we are mixing equal amounts of streams containing A and B, and the sum of these two volumetric flow rates will be the total volume that enters our tank, our mixing tank, in any particular time. So we have this now. Now, in our required information for the problems, I'll write it here. What are we required to determine? You are required to determine the number 1, what is required? Okay. You are required for the concentration. The concentration of the what? Concentration of the, so you are required for the concentration of R at the exit of the PFR. Okay, so if it's at the exit of the PFR, all you have to do is label it properly in here and then place it on the required part of your solution. So you can place, if this is CR prime, or you can place here, if you don't want to use the CR prime, then you can use CR1 because it came from the first reactor. Then this must be CR2. Okay, we do not know this. But in terms of what the problem required, I'd like to read the statement again. It says here, what is the concentration of R at the exit of the PFR? So based on our labeling, if it's at the exit of the PFR, then you can write here C sub R2, because that's how we labeled it. So it's dependent on how you label that particular unknown in your given. Then the second requirement is, as you have placed on the chat box, it says that you are to determine the overall, or that is the conversion of A in the system. So it's referring to the overall conversion of A in the system. So we can place here in our another required information X sub A. So I did not label it as 1, as 2 based on the reactors here, but X sub A, meaning it's referring to the overall conversion of A in your system. So your system constitutes of the PFR and the MFR. Okay? Now, before I go to the solution, do you have any questions so far as to what we have written here on the given and required information? Okay, so there's none. So we go to the solution. So we want the concentration of R at the exit, and we want the overall conversion of A in the system. So what do you think if I'm going to ask you, what would you solve first if you are the one solving this problem? What would you determine first? Okay, any suggestion? What would you determine in this case first? Since you want to know CR2 or C sub R2, and you want to know the overall conversion of A in the system. By the way, I'd like to label this as CAO prime, and this is CBO prime. Now, we can't label this as CAO and CBO properly because the CAO and the CBO already refers to the initial concentration of A and B in the system inside reactor 1. Now, whereas this concentration here of 0.020 mole A per liter and 1.4 mole B per liter are concentrations of each of the streams that are introduced into your first reactor. Okay, so we cannot label it as CAO and CBO based on our nomenclature because CAO and CBO should represent already the initial concentrations of A and B, respectively, in the system inside your MFR. So based on the changes I've made on the representation of the given, what do you think would be the first step that you ought to do in your solution? Okay, since we are given the concentrations of the streams, you need, of course, the initial concentration of the system that is expected to react and produce R in your MFR initially, because there's a mention that there is 0.002 mole of R per liter formed in the mixing tank. So where this particular mole of R came from, we need to know the initial concentration of A and B in the system already. So your CAO, since we have equal volumetric flow rates for stream A and stream B, just like in the previous problem that was discussed to you, would be equal to 0.02 divided by 2. On the premise that you have, let's say, 1 cubic feet per minute or 1 cubic feet per hour of stream A that enters, and another cubic feet per hour of B. So the total volume for your system now will be 2 cubic feet per minute or per hour. So that would give you the concentration of your A in the system already containing A and B. So it has to be divided by 2. In this sense, the initial concentration of A in the MFR would be 0.01 mole A per liter. You do the same for B, because you cannot use the concentrations that are given in the problem because these are concentrations of the streams, not the concentration of the mixture already. So for B, you ought to do the same, 1.4 divided by 2, and that would be 0.07 mole of B per liter. These are the initial concentrations of A and B now in your MFR. Now, the next thing that you ought to do, since in your system, you have here for your first reactor, the MFR, and then you have the second, the PFR, you are to write the performance equation of the MFR first because it's the first reactor in your system. Should it be the PFR, then you are to start with the PFR. So whatever is the reactor, the first reactor in your system, that's the first reactor that you're going to write your performance equation. Because from there, you would know what are still the lucky information that you ought to find, or what are the information coming from this particular system that would be beneficial or that would be very important relationship or value or equation in your next reactor. So in that case, you will have to start with the MFR. So right here for MFR. MFR/mixing tank. Your performance equation for the MFR is, of course, the space velocity, which is actually V of the mixed flow reactor divided by the volumetric flow rate, and this is equal to CAO XA. In our representation, that would be CAO XA1 because it's the conversion in the first reactor. Then we divide it by the rate expression. But it has to be specifically also written with the subscript 1. So meaning you are to write the rate law based on the concentrations that will be used for reactor 1. Okay, it's a different thing if you're referring to reactor 2. So in our case, we're going to substitute value now. So volume will be 1 cubic feet. So you have 1 cubic feet here. And we do not know the total volumetric flow rate. So that would still be V. Okay? And then your CAO, XA1 would be actually your CAO here, which we just determined, 0.01. And you have here XA1, the conversion in your first reactor. Then we divide by. So how will you represent the rate law on the first reactor? So that would be K CA1, sorry, CB1, I wrote B. So this would be CB1. Okay, so now we will write down, you have here, this K is a constant. You can place it in here together with the V. So I'll have here a K over V. Okay, transferring the K here in the numerator on the fraction here on the left side. So just like this properly. We'll have K divided by B. Okay, what is left here is your point. Now, there is actually, shall I say, an alternative expression for CAO XA1, and this is suggested when you are dealing with multiple reactors, and that is, you are to write the performance equation for a mixed flow reactor in terms of concentration. So if you're going to look for an equivalent expression for CAO XA1 without having to determine XA1, because if you notice, if this XA1 stays, you will have another XA1 here in terms of the CA1 that you have in the denominator, and the CB1, you need again to express the XB1 in terms of XA1, and that would be cumbersome. So you can rewrite, there's nothing wrong with writing it here because anyway, that's your performance equation, but you can rewrite this expression in terms of concentrations, not conversion, as suggested by Levitt's field. So your CAO XA1 actually in terms of conversion is what? In terms of our representation, that is actually your CAO minus CA1. The initial concentration minus the remaining concentration unreacted represents the amount that has reacted. So your CaOXA1 can be represented as CaO minus Ca1. Now this rate expression that you have here can be written as K rather Ca1 Cb1 as well. Now here in the denominator, we will simplify further our denominator here on top. So I will place here CaO minus Ca1 divided by K. I still have Ca1 here, but this CbO, you can recall, this Cb1, the B left from your first reactor would be your CbO times 1 minus xb1. If I'll have this CbO distributed here, the resulting expression will be CbO minus CbO xb1. Now, we have discussed this several times already. Then when you have 1:1 or 1 mole of A reacting with 1 mole of B, this amount of B that has reacted would be the same amount as A that has reacted because of the stoichiometric equation. What am I referring to? So we have this very fundamental relationship taken from our stoichiometric equation. It's all divided by 1 because stoichiometrically, this is your chemical reaction. So the amount of A reacted is just equal to the amount of B reacted because 1 mole of A reacts with 1 mole of B. Now, what then becomes of this? So I will simplify it here further. So I'll just erase this. Now, the CaO, Ca1 represents actually this one. Okay? But if I will place here another equal sign, you will notice that the CaOXA1, which is equal to CbOXB1, is equal to CrOXR1. The amount of R that was formed. I say that was formed because R is a product. So you don't say anymore that has reacted. The amount of R that has formed in your mixing tank or in your MFR, which is your first reactor. So I can replace this, which is equal to this, by this one. Okay, because this is just divided by 1 as well. Do you follow? Your CaO minus Ca1, which is equal to CaOXA1, can be replaced by CrOXR1 because of this relationship taken from the stoichiometric equation. So I can now replace this by CrOXR1. Okay? And my denominator now is, so I already transferred the K here, so I will have Ca1, the part of A remaining, and I will have CbO minus CaOXA1. Where am I getting this? From in here. CaOXA1 is CbOXB1. Okay? Now, this is your performance equation from the mixed flow reactor, which we can still simplify. So I'll write it first here so we can simplify further. So you have K divided by B is equal to CrOXR1 divided by Ca1, and you have CbOXAO-CaOXA1. Okay, that's the equation that we have in here. So we can have continuity and place it here again. Now, what is this CrOXR1? You say this is the amount of R that has the amount of R that was formed. Okay, that was formed. Now it's already known. So we have K over B, and we know that the amount of R that was formed in your mixed flow reactor is 0.002. This is the amount of R that was formed. We don't have R initially present. So then the amount of R that was formed in here will just be the amount of R that leaves your MFR. So this is 0.002. Now, what about CA1? The amount of R left, right? So what would be placed in here for CA1? The amount of, rather the amount of A that is left. What would you write it down? Or how would you write it down in here? Another alternative equation that you can replace CA1 with. That would be CA1. The amount of A left would be, so just like this one, your CA1 is CaO1 minus XA1. Your CBO, you already know to be 0.07. Your CaOXA1, based on our relationship here, your CaOXA1 is CROXR1. So that would be this one, 0.002. Okay, feel free to interact if you cannot follow through. So we'll have K divided by V is equal to 0.002. And we will have this one, 0.07 minus 0.002. So this is 0.068. And this, we are left with this one. What is this? This is actually CaO minus CaOXA1. I'll divide this by this. You'll have 0.0294. And in my denominator, my CaO, which is 0.01, this one, minus the CaOX1 again, we go back to CROXR1, and that would be 0.002. This one, the amount of A reacted is the amount of R formed. So we have this. So we have a K over V expression, which is, so your 0.0294 will be divided by the difference of 0.01 and 0.002. Now, this will give you a 3.6765. Okay. Okay, so let me check, huh? Okay, we will check our computation, our substitution, so that you can follow through again. So this is our mixed flow reactor performance equation. This is our performance equation. Okay, everybody knows how to write the performance equation of a CSTR. The amount of A reacted was changed to an expression, which is the initial amount minus the final amount. Okay, initial minus final is representing the amount reacted. Your rate law is represented correctly in this manner. So K, CA1, CB1. The remaining amounts of A and B, respectively, for the concentration of A and B. Now, we substituted the volume. You have the volumetric flow rate. And initially, we place the initial concentration of A and replace XA1 next. The problem with this, as explained a while ago, is that it's in terms of conversion, and that will also require you to express your concentrations for A and B in the denominator in terms of this same conversion. That would be taxing. So we have to replace your CaOXA1 by this expression here. Okay? Now, for the denominator, you have still KCA1, we copied it, and CB1, the remaining concentration of B unreacted in the MFR is represented as CBO times the quantity 1 minus X sub B1. Now, you have that. However, this CaO minus CA1 which represents the amount of air reacted, represents also the amount of R formed based on the stoichiometric equation. So we replace these two concentrations here, the difference of these two concentrations in terms of the amount of R formed. Now in our denominator, we already have Ca1, we have CbO, and we change the CbOxB1 to CaOxE1. Again, going back to stoichiometry. The K here we have transferred on the left side. So we have now everything here. The amount of R formed is given to be 0.002. And the Ca1 here, the remaining concentration of A in the first reactor is CaO, 1 minus Xa1. The CbO was substituted, and the CaOxA1 is also the same amount of R that is formed. So we substituted, and then we have determined the difference here of 0.07 and 0.002. So this is the answer. Your numerator is 0.002 divided by 0.068. And you have here CaO minus CaOxA1 if you distribute the CaO. Now your CaO is known to be 0.01 and your CaOxA1 is 0.002. The same amount of R that is formed in your MFR. So kindly check if my value here is correct for the K over V. Is it correct? The 3.6765 starting from the value that we have in the numerator. So you have 0.002. We divide by the difference of 0.07 minus 0.002. And we divide it further by 0.01 minus 0.002 for CaO minus CaOxA1. So you'll have 3.6765. So this is okay already. Now you may check, you may ask, what about the K and the V miss? We don't have specific values for this, so what we'll have is just an expression of these two. Okay? Now we'll set up another equation. Is this my first? Okay, this is our first reaction. So we'll set up another equation for the PFR. Okay, for the PFR, what is your performance equation? Your tau P is equal to the volume of the PFR divided by the volumetric flow rate that is being processed by it equal to the integral of CaO dxa over, you have the rate. Okay. In here, your conversion would be from XA1 to XA2. Primarily because this is already your second reactor, so your second reactor rather. So you will have an initial conversion here of XA1 and you will have a final conversion of XA2. Now, if you substitute the volume of the PFR, that would be 4, and you'll have it divided by B. The CaO you can place before the integral sign. Now, if you recall our discussion regarding the PFR, we should express our computation here in terms of conversion, not concentration. Okay, so we'll have here K, and for this particular reactor, we have CaCb, general representation, and you will have XA1 here to XA2. Now this K, the same rate constant that appears in the PFR could be written here, class. So I can write now this expression as 4 times K divided by V. And the CaO, this is the CaO class, the initial concentration of the stream that enters already your PFR. So what is the initial concentration for the PFR? If I may ask, what is the CaO for the PFR? because this one is a generic representation. In terms of your PFR, what is the initial concentration that enters it in terms of A? If I may ask, is it still CaO? What's the initial concentration of A of the stream that enters your PFR? Are you there, class? Is this still CaO? Should I write this as CaO or should I change it? Because we are now on the second reactor, which is the PFR. No idea? What's your CaO, the initial concentration of the streams that is being processed by your PFR based on our representation? If I will label this as Ca1, this is Ca2. So how will I write this? What's the CaO for PFR? Jelaine, what's the initial concentration of A for the PFR? Are you there, class? Jelaine, are you there? What? You don't know. So anybody who knows what would be the initial concentration of the stream that is being processed by your PFR? Would it still be CaO? CaO is the initial concentration here. Okay. What about Ca2? Initial concentration Ezra. Ca2 is already the final concentration of A that leaves the PFR. It should not be Ca2 because it's the final concentration. What should it be? Via, what is the initial concentration?
Not sure, Miss, pero 0.008.
0.008. Where did you get the Diha? Ang 0.00.
0.01 minus 0.00.
So you're telling me that your Ca1 is the initial concentration?
Ano, Miss? Ang gin-minus ko, Miss, ang 0.01 sa 0.002. Pero hindi ko sure.
If you're going to subtract 0.01 to 0.002, it would be negative.
Yes.
It's very simple actually if you're going to look at it on the schematic diagram. What's the initial concentration of air as it enters the PFR? What's the initial concentration? Isn't it Ca1?
Yes.
The CaO is the initial concentration of these two streams already. That is means that enters your MFR. So the initial concentration of the stream that is being processed by the PFR is this Ca1. If you're going to write it here, if we stick to conversion, we'll see this CaO will not be CaO, but this is just a generic performance equation for the PFR. But if you're going to have it specific to our problem, this would be Ca1. Okay, the initial concentration of the stream that is being processed in your PFR. Now there's an alternative here, class. That way you won't have to deal with conversion. Since you could see here that you will have XA and you need to represent your Ca here in terms of XA. And in the second term, as I have explained also a while ago, your CB will have CBOXB, and you need to express your CBOXB in terms of CAOXA because your unknown function here is XA. Hindi siya ma-process ang integral kung naka-CBOXB ka din, tapos ang XA di sa babaw. Now, there's nothing wrong with, I'd like to specifically write this one now as CA2, CB2, okay? The way it should be in terms of our PFR, our second reactor in the series. But if you want to use also concentration, you can do that. Now, there's an alternative in terms of our performance equation for a plug flow. I'll just write it here as a separate case. So this is our space-time for the plug flow, and you will have here, this is our original performance equation for plug flow, the generic that is without subscripts. You can represent this also in terms of conversion. How would you do that? That CAODXA, if we can recall, where did this came from? Din siya naghalin. Ang CAODXA. Isn't this also equal to negative DCA? I'll show you. So you will have CA equal to CAO 1 minus XA. Right? If you get the derivative of this, that would be this one, you also get the derivative of this. The derivative of that expression. So you'll have DCA is equal to, this being a constant you can place before, the different derivative or the differential representation, and you will differentiate 1 minus XA. The derivative of 1 is 0. The derivative of negative XA is negative DXA. So if I'll make this negative, I can also make this negative. So I'll have DCA is equal, or negative DCA is equal to negative of negative will be positive. Do you get it? So we can represent in the original performance equation of the plug flow the CAODXA by negative DCA. Do you get it, class? So that you won't have a problem with conversion here, because this will be your big headache, the conversion here. Oh. You have to change the CBOXB here in terms of conversion, and we do not know that. It's good if the problem gives you that, but since the problem did not give you the conversion of B, then it's best that you express the performance equation of a plug flow reactor in terms of concentration rather than conversion. Although originally, amo gini siya ang performance equation sa plug flow reactor. Do you get it? Do you understand? Before I proceed.
Yes.
So I'll clear this frame na. Sige, we'll keep it there so you will, we can go back to that later. So this one actually can be changed in a simpler, I'll just place your equal also. Place the equal sign. Anyway, this K is the only thing that you cross-multiplied in here. This 2 remains. So I can place here negative. So look here. Negative DCA is this one. Okay, so I need to place the negative sign. Negative of the integral of DCA. Then instead of writing KCACB, I'll write na only CA CB. Now, I have already concentration, so this would be CA1 to CA2. The initial concentration that is being processed by your PFR is CA1. Its final concentration is CA2. Now, in the way it's represented in here, we still have one more problem. And what is that thing that is our problem in here? Ano pang problema ta? I'm going to ask you, can you already process the integral as it is? Can you process the integral as it is? Can I keep the CB here? Yes or no? You're done. You are all done with your DE. Can I keep the CB in here? Hmm? The answer, of course, is no. Thank you for that, Vincent. Hindi pwede i-keep ang CB. Kaya imo unknown function is CA. It's just like you have X, and this is Y. So you cannot have this evaluated. I'm referring to the integral. So what do we do with CB? So we have to what? I'll write use another sheet here. So originally, our CB is equal to, generally, this is how we represent it. CBO 1 minus XB. Okay? And it is CBO minus CBO XB. This CBO, we don't have any problem with that because it's a constant. Our problem is in here because I am given an integral. In this case, I'm given an integral which has an unknown function which is CA. So what do we do? I change this one, of course. So I will have CBO minus CAO XA. Okay. Now, what is the CAO XA? That's CBO minus what is CAO XA in terms of, let's say, CAO and CA1. CAO XA is CAO minus CA, right? Why, miss? You have here CAO 1 minus XA is equal to CA. CAO minus CAO XA is equal to CA. CAO XA is equal to CAO minus CA. Do you get it? So the C sub B that I need here should be now like this. C sub B is equal to C sub BO minus C sub AO, negative, negative, plus C sub A. Do I know this too? The answer is yes, because this is the first thing that you did determine. So your CBO is 0.07, your CAO is 0.01. Then we'll have this one as 0.06 plus CA. 0.06 plus CA is your CB. You can go back to here. 0.06 plus C sub A. The CB was changed to 0.06 plus C sub A. Do you get it, class? Do you have any question? Wala. Ini siya, class, na representation, naging present ko sa inyo para ni siya sa CBO, 1 minus XP. The CBO and the CAO, remember, is the initial concentration in the MFR. I intentionally wrote it here to check whether you can really follow in principle what we are doing. This one is for the CBO and the CAO of the MFR. Now we're talking about the PFR because we're making a performance equation on the PFR, which is our second reactor. So actually, In terms of the form of the equation, everything here is correct. But this is applicable only for the first reactor because we're using CBO and CAO of the first reactor. We're now talking about the second reactor. So if it's the second reactor that we're going to talk about, what then would be the changes here? If I'm going to ask, anong ma-change dire? Kung nakuha nyo ang principle, kaina nga din pa-change yung one ang concentration sa PFR nga initial. What then should be written here for this one? This one is for the MFR because this is CBO and CAO of the MFR. Now, when we talk about the PFR, what should I change here? Ang mumani siya gyapon ang form actually, I intentionally wrote it that way. Ano lang i-change ta? Ano ang i-change natin? Because we're now talking of the PFR. What do we need to change? For the PFR, I write here PFR. This one is for the MFR, so you will have a basis. You set up a CB expression in terms of C sub A, now in the PFR. This is for the MFR. What should it be? Okay, I'd like you to take a screenshot of our entire solution. Okay, I'll start with the solution here. Start with the given. Take a screenshot of that. 1, 2. Then in here, 1, 2. Then we have here 1, 2. This one, the one I wrote here is the expression for the MFR. This is not for the PFR, so I will change this. We still need a representation of C sub B in the PFR. So I'll take that one out here. Take a screenshot, please. This is still the thing that we're looking for. 1, 2. These are the different derivations that we use. Converting CaO dXA in terms of negative dCA. And this one. But this is for the MFR. Now tomorrow we will continue, but I will be the one to ask you what would be the C sub B expression in this time, the PFR. And that's the expression that you should write in here. That way you can integrate. This K over V, you remember this K over V is this K over V that we have here. So it's now a constant and we can place it just in here. So the remaining goal for us is to determine the concentration of C sub B that should be placed here. That way we can process this and answer the required information in the problem. So we will again continue tomorrow, and that will be your assignment. How will you write the expression for C sub B in the PFR using this principle illustrated to you in the MFR? Okay, so I will not just check the attendance today because a lot are absent because of connectivity issues. We will continue this tomorrow. It's already 1:33, so we will just continue this class tomorrow. Do you have any questions?